Okay, good morning all. Thank you for joining this session, this side event and here we'll be talking about AI4EO Map Your City Challenge. So I hope that you will get excited by this upcoming challenge. So what will be this session about? So you will learn what is this Map Your Cities challenge. We'll go through the data set that we have created for this challenge. Then we'll introduce the EO-TDL platform, which is the Earth Observation Training Data Lab platform created by ESA. And then we'll go through the notebooks. We'll provide recommendation on how to use this data set, how to do machine learning and deep learning model with this data set, and then we'll encourage you to participate to this challenge. And then we'll leave room for Q&A at the very end. I'm Nicolas Jepe, I'm with the ESA Lab. And this session will be mostly made by industrial partners, starting from Space Tech Partner with the prime and lead of the AI4EO Challenge project. And then today there will be speakers as well from Minders, which is a company in Switzerland, Synergize and Earthpulse. And with that, we leave the floor to Michael that will introduce what is this Map Your City Challenge. And I hope that you will enjoy the session. So, over to you, Michael.
Hello, my name is Michael Hyland. I'm a senior consultant at Space Tech Partners. We'll have a brief company introduction later in the presentation, so for now I'll just get into the competition itself. So the AI4EO challenges, there's challenges that have been done in the past, and this most recent edition is, so hashtag Map Your City is how we stylize it. And it's based around the idea that we need a better understanding of urban environments for better actions. Whether this is new policy coming out, something like the Green Deal, or it's from the private sector needing this information for things like building repair, a city for regulation, safety and welfare, and even tourism and heritage. So within understanding an urban environment, there are many variables, of course, but one that is very predictive is building age. And so this Map Your City challenge is built around the idea that building age is such an important piece of knowledge for so many sectors that it should become a focus. The details of the prize, which should be interesting to most, is that we have an indicative prize of about 5,000 euros, and we're still working on some other ones, so whether that's spread over first place to third place or other things. Right now, the deadline looks like it will be the end of March. Moving on. So why join one of these challenges? There are plenty of reasons besides that, of course, great sum of money and that incentive. We see that even people with complete beginner knowledge who join this, they can join teams, they're pushed to have exposure to this knowledge. So with any background or any experience, joining one of these challenges is right away going to put you in touch with first ESA's Phi Lab, other people who are interested in this. If you're an expert, you can help beginners. If you're a beginner, you can learn from these experts. And all of this mixture around the challenge is a great ecosystem. Additionally, we have the AI4EO community on Discord, and that's another great way to exchange ideas. Another great aspect of this is we see people market themselves. So ESA has great branding, whether it's the colors, the logos, the LinkedIn posts that will happen, and you can very easily share it to your story and your network and make it clear that you're a part of this effort and this community and these challenges for cutting edge technology. I won't go into more detail as we go through each section of this, so right now I'll pass over the floor to MindEarth to introduce some of the data sets.
So good morning to you all. It's a pleasure to be here. I'm Mattia Marconcini from MindEarth. I'm a co-founder of this company that we established at the beginning in 2018 as a non-profit association in Switzerland, and we started serving international public agencies with mostly tasks related to, let's say, humanitarian and development application, and especially collecting and analyzing bigger data. And for instance, we had the chance to work in tasks concerning large surveys on the field, population exposure, hazards, demography. And in 2021, MindEarth became actually a for-profit company, especially with the goal to translate what we've been doing with the public sector also in the commercial field, in the industry. And we serve the different topics, more related, let's say, to the B2B, others more related to, let's say, open international organization, government and public sector, humanitarian development, mobility and transport, but also real estate, retail, and consumer insight analytics. To summarize it quickly, Mindearth works at 3 different scales. We work at the global scale with Earth observation imagery, especially satellite data, where we perform, say, special inference, especially using advanced machine learning, deep learning. But then we also work, let's say, at the regional scale. For instance, we target a lot mobility. We work a lot with high-frequency location-based data that are collected from mobile phones and that enable really systematic retrieval of key information on the mobility of persons. And also at the local scale, we developed our own devices for performing a street-level survey, which consists both in, let's say, a low-cost device with a 360-degree camera, and more recently with an application that will be released also publicly very soon on both on the Apple Store and the Play Store, where anyone can turn into our eyes. So people can download the app and start, let's say, doing crowd mapping, and me reward about that. And we had the pleasure to be involved in this activity, and let's say where, quite a lot of our expertise, let's say, fit, especially because we're talking about street level imagery and satellite data. But coming back to the purpose that was introduced briefly, we are targeting building age, and the concept of building age is pretty easy. If you look on the dictionary, it says that it's a time elapsed from when the date the building was built. But actually, it's something which in the practice, it's way more complicated. Here we see, for instance, a very nice excerpt of this graphic novel from Vincent Mahe that described how a given building changed throughout history. So these are just some glimpses, but it's pretty nice because it shows, let's say, from the 13th century to present, how the building has been reconstructed, adjusted to the time, because we have to remember that at the beginning, architecture was mostly focused on the needs, let's say, related to safety and security. But throughout time, other factors became more important, especially recently concerning comfort, concerning also beauty and technology. So why is it important to know about building age? Well, there are several people that are really relying on this information, ranging from historians to urban planners to governmental, environmental responsible people. And for instance, we know that related to the heritage, knowing the age is important to determine the historical significance and of course to preservation. In the urban planning, again, it's relatively easy to assess to knowing the age that let's say allocate resources for renovation. Let's say the more old the building is, the more preservation and let's say dedicated resources are needed. In the terms of real estate, it's pretty interesting because it's a key factor to determine the values. So we know that older buildings tend to have maybe lower prices because they are less new. They have some issues that are due to the time, but very old buildings instead have a very high value. So it's actually something not really linear here. But also related to taxation and property records, it's important to know about the age of the building because it enables to assess property taxes and maintain also the related records. And definitely, last but not least, it's a key factor to assess the energy efficiency and the environmental impact of the different buildings. Here, for instance, it's something that is an example that relates to the city of Milan. And especially we know also from the latest EU regulations that it's important that every building has a sort of an ID related to its energy performance. which are becoming mandatory at the European level at least. And we can see here the distribution of the age, of the related energy performance, which ranges from A, more efficient, to G, least efficient, throughout time. So it's in Italian, but we know that, for instance, before 1930, the vast majority of the buildings were definitely not compliant with any energy efficiency regulation. You see the deep red, and they correspond to what now is categorized at class G. But then we can see that through time, and we identified bins that mostly corresponds to also the introduction of specific policies. This definitely changed, and we can say that a big difference happened after 2006, when, let's say, more strict regulation were put into place, and where from that time on, the vast majority of the buildings, at least, is more compliant, and it's mostly in classes A and B. So where can we retrieve information on building age at the larger scale for Europe? Well, recently there has been a new data set published not later than a few months ago. This is called the EOBUCO, and it's a common and open database that collects, as it says here, the European building stock characteristic, especially from governmental and authoritative sources. So here, interestingly, this data set that is open and free covers 28 countries, and it includes building outlines for more than 200 million buildings. And it also incorporates additional information related to height, type, and age. And if we consider, for instance, the countries where at least there is available information for more than half of the buildings, we can say that data are consistently available for 14 countries, the building type, so if it's residential, industrial, etc., for 7 countries, and the age actually is the least covered, where just 3 countries are actually sharing through authoritative data sets information for more than half of their buildings. And here we can see an example, despite Austria is really advanced, and I mean, there are several data sets that are openly accessible through, let's say, different national portals. On the left, we can see that we have a lot of height data. Basically, here there's an example of Vienna. All buildings are provided, are associated with their, let's say, average height here. But concerning age, we basically have nothing. So this is something that, of course, stresses the need for getting, this type of information. And how can we estimate building age? Well, there are different possibilities with different data sources. We can think about street level imagery, and of course, this is probably the best way for several reasons, because it provides really a detailed view of the front of the building, the facades, and here, based on the analysis of the specific materials or architectural style, we can understand the status of the age of the building, and what's also called wear and tear. So wear and tear, it's kind of an indication of the sign of the time. There are buildings that are relatively old, where we can imagine that the painting color is fading away because the aging, and it's maybe not properly preserved, or even the appearance of different cracks. And where can we access this information? You're all familiar maybe with Google Street View, but unfortunately, if you want to use Street View data, this is not really accessible because of several limitations in the usage outside Google application officially, because people do it, but it's not really possible formally. But luckily, there are other open platforms like Mapillary, which is actually currently owned by Meta, formerly Facebook, where a lot of people, let's say, on a voluntary basis, upload information and imagery of street level, and they are publicly accessible. There are some cons, especially because we can have occlusions because of the presence of trees, vehicles, or even in narrow streets we don't have a proper view of the upper part, and definitely the major limitation is also due to the coverage, because not all the areas are actually covered by street level imagery. But then we also have an ideal view from above, and say we're here and we're all familiar with satellite imagery and orthophotos. The pros are a clear and detailed overview that is useful, especially to identify roof materials, condition, and also the presence of items that enable us, say, specific understanding. For instance, if we see solar panels or the presence of a green roof, this is actually a clear indication of, say, probably high energy performance. They are definitely accurately orthorectified, so geometrically corrected, so we know that what we see is exactly where it corresponds on the ground. But yeah, we know about the cons that are mostly involving, the cost of this imagery that often are expensive, very expensive, and the temporal resolution, because they might be not very up to date, and this might lead in some cases to outdated information. But also we have the Sentinels as a representation here of the, say, medium resolution, high resolution imagery that are freely available, easy to access, and especially these are extremely suitable for large-scale analysis. In the case of the Sentinel-2, we go down to a resolution of 10 meters, which is definitely good. But if we want to do analysis maybe at the building block level, this actually detail prevents identifying features related to single buildings, and of course we cannot capture small scale variations. But here is actually what we are targeting. What if we provide you with concurrently street view imagery, very high resolution orthophotos or satellite data plus medium resolution data? So is the combination of these three elements allowing us an improved estimation of single building age? That's exactly what we would like the participant of this challenge to target. And the objective is really stated there. So really the goal is to leverage on an heterogeneous but consistent data set that have been thoroughly prepared during the last few months. And the goal is really to train a multi-modal deep learning that allows, say, an improved and reliable estimation of the construction year. And here, these are some details. You will have more in the following by the following speakers during the presentation. But we will provide you with overall more than 35K buildings that are located in 19 different cities, spread over 6 different countries. So you can expect kind of heterogeneity, because the style and the architecture of the buildings really changes. We don't tell you which these are to make it more spicy. And for each building, you will have the following information. So we provide you with the age, which has been in the same groups that were shown previously for the example of Milan, that are, let's say, roughly divided in the bins of 15-year time frame starting from 1930. And the closest street view image that depicts the building facade, and concurrently, let's say, the two top views. One, cloud-free at 50 centimeter resolution, and here we will be given, say, a patch of 256 meters, so corresponding to 512 by 512 pixels, and a cloud-free 10 meter resolution Sentinel-2 based patch, which is 64 by 64 pixels, of course, corresponding to 640 by 640. And both of these are centered at the building facade. Regarding the input data, as I mentioned before, we at Mindart also implemented different tools to collect street level data. So this is also part of the data set. So where we had our crowd, say, performing on the field missions with both the 360-degree cameras and smartphones. And also we relied on the freely available database from Opillary. And here Any picture that you can download is also provided with metadata, including details on when it was captured and also the specific type of the camera, and also the position and the direction of acquisition. And here, a bit more detail. I mean, it's a bit more technical, but I'll try to keep it light. So how did we manage to extract the exact crop, including the building facade? First of all, we considered, let's say, as I said before, the available imagery from our database and mapillaries, and we took into consideration the Obuco dataset, where we had some age information available, and we did the coupling. So we started considering areas where at least some age information which was retrieved from authoritative sources was accessible. And then for each building we defined a dedicated view cone. So you can imagine that maybe when you walk by you can start seeing a building, but of course to appreciate its facade you need to be at a specific angle. So for each building we defined let's say a cone that ranges from 45 degrees to 135 degrees, and we subsetted all the street level images that were basically intersecting with this cone. And then we actually let's say filter also based on specific criteria, because it could be that maybe you are, say, too close to be capable of understanding, to view the facade. If you are 2 meters apart, there's no point. So the range that we selected was between 10 and 50 meters. And then, since we had information about the direction of this photo, we started performing the cropping exactly in the direction of where the facade is. And then we had to check if there were occlusion or not, so we performed automatic computer vision segmentation based on deep learning models, and we selected then, among the others, the crop where we had the let's say the highest percentage of the facade that was included, and last but not least, we also performed some photo rectification. Related to the very high resolution imagery, here we consider two different sources, as I introduced before. So we had a very high resolution satellite imagery, specifically available from the ESA third-party mission program. Here we consider the one from the archive, and with a resolution of 50 centimeters, and orthophotos. So it's interesting that luckily now more and more countries in Europe are systematically acquiring orthophotos with resolution, with a detail that mostly ranges between 7 centimeters and 20 centimeters. And these missions are performed mostly in spring with a repetition of 2 years. So, and more and more countries are doing it, and especially they're putting it out for free. So we could rely on this data set and then resample everything at 50 centimeter, for consistency. And importantly, all the imagery that was taken refer at least to 2017. And since, say, our last bin is, in terms of age, is from 2006 onwards, it's definitely fitting with the purpose. And then how could we determine where to center our top view imagery? We did this simple exercise. So for each building, out of Obuco, we extracted the corresponding centroid, and then we had the position of the street level imagery that was acquired again from Mapillary or from our database, and we established the link between the acquisition point and the center of the buildings, and we selected, let's say, as a reference point the intersection of this with the closest facade of the building, and this corresponded to the point where we really centered our orthophotos and Sentinel-2 data. So you can see here again in images, we access the very high resolution orthophotos. We resample it to 50 centimeters. We add the center point from the analysis that I've just explained, and then crop it to 256 by 256. Similar exercise was done with Sentinel data, as I said before, for a data set, a neighborhood of 640 by 640, and more details about the Sentinel data will come by my colleagues in the rest of the presentation. So, if the floor to you guys.
Next, we'll introduce the EOTDL, which is the Earth Observation Training Data Lab. First, a bit about Space Tech Partners, the company that I work for. We're a consultancy that's completely focused on the space sector. So here you can see that there are 3 practices in the second column: strategy, innovation, market development, 2 locations in Munich and Brussels, and a team of getting closer to 50 people now, but 20 to 25 different nationalities, so an exciting place to work. And 18 languages, of course, is very helpful. Our work is, even though based in Europe, very international. And over 15 years of experience in the market. So my personal background is in Earth observation, specifically for international development. I'd like to introduce EarthPulse, the other main partner here. And the vision of EarthPulse is to use satellite analytics accessible, easy, and useful for all. And you see that goal will come across in the Earth Observation Training Data Lab as well. And you can see here a typical suite of AI-powered satellite analytics at your fingertips. And with that, directly into the EOTDL. So the motivation behind building a training data lab was that we see such great advancements happening in AI, whether that's image recognition, image segmentation from these models, to our generative AI that everyone's already probably very familiar with. A lot of what powers this is the training data. And what we saw is that these exciting advancements, despite having petabytes and petabytes of satellite data, that there's a certain bottleneck about getting to these really amazing results just because the training data is so difficult to compile and to annotate. One of the best data sets out there, let's say Google's Dynamic Earth, it was 40 people for 3 months labeling by hand. Is this a forest? Is this, is this a street? Something like that. And even then, it's not perfect because maybe it's actually a eucalyptus plantation and it's labeled forest. And so the training data lab, the idea is that we can put all of this together, and we can put it together with something called Stack, which I'll talk about briefly next year. But the EOTDL, you can ingest your data source, come into the standard structure, and also access other people's data source. And we're hoping that we'll build collaboration and really lower the hurdles for what seem to be compartmentalized sources. In the end, right now, this is today the debut of the EOTDL, but the full functionality will have combining, annotating, and quality checks. Of course, we have a GitHub and a Discord, so I'll show you that link later, and I encourage you all to join, especially in this exciting part where we're finishing the development. We're really looking for user feedback. And then there's ready-to-use models to train and deploy. And of course, ESA's been generous to grant us some cloud computing, which can also be requested in the Discord. We'll use the EOTDL to host this data set, and we'll be one of the first competition data sets hosted on there. So we're looking forward to it. For those who aren't familiar with Stack, Stack is a spatio-temporal asset catalog. It's in a JSON format. Here, if we go right away to this green box in the structure, it seems simple, but the real beauty of it is that it's a bit like lazy loading. So you can do a lot of actions to cut down from this petabytes of information. Let's say you're searching for the entire city of Vienna, and you're at more than a gigabyte, or could be even more, it could be 10 gigabytes of data. Maybe your actual region is much smaller, and you can use Stack to focus on what missions, what dates, what bands, what area, and you can get down to something manageable that maybe I could even run on my work ThinkPad here with like 8 gigabytes of RAM. So this is an exciting, enabling data structure. And the way I think about it is you can test the water before you jump in. You can build your model, you can select what you need exactly, and then you can execute. Now that's how we do it with satellite images. The idea of the EOTDL is that we can do that with training data as well. So we don't need to load an entire global data set if you only need the training data from Germany. So typically how it would work right now is you would apply the model that's been trained globally on your region, and that would be the sort of simple way to do it. With the EOTDL, we want people to sort of repurpose that data. So to subset a global data set with a local data set, with a regional data set, then select the images, then run your model. And this should all be more lightweight and more dynamic. We'll have a Q&A session at the end, of course, if people are interested. So the EOTDL will support the challenge with, first of all, access to the challenge data set with the command line interface or library. So it's an easy sign up with an email on the website, and the access is free. So here you can see with those with programming knowledge, here's some basic use cases. And we'll have a cloud workspace to train your model in the cloud. And if you join us on Discord, you can request GPU access. And here's the link for that. This will also be shared online. And we will be having a demo on November 8th. So in the demo area here at 6:30 or 18:30. All right.
My name is Nika Oman Kaduns. I'm from the company Synergize. First, short introduction. So our company is a partner in the AI4EO challenges. And the company was founded in 2008 in Ljubljana, Slovenia. And we have more than 15 years of experience in the GIS sector. And what we do, we are the developers of Sentinel Hub. We also develop tools for machine learning workflows. And I will present our newest project, also in partnership with ESA, for machine learning extensions of Sentinel Hub. Then I will talk about our role in AI4EO challenges and present the notebook we prepared to help you start it with this challenge. So Sentinel Hub, maybe some of you know it, is a cloud-based data API that enables easy access to satellite and other Earth observation data collections. The data can be accessed through various APIs depending on the purpose and the type of data you are looking for, and can be accessed either programmatically through our EO browser or through GIS applications. On Sentinel Hub, there are many data collections readily available, including I will emphasize here the open satellite data with all the Sentinel-2 Sentinel missions, and also the Landsat missions and others. We also develop machine learning tools to enable the machine learning workflows. This is the EOLearn library, which is an open source library, and enables the full workflow of machine learning applications for Earth observation. And also for the scale-up, we have the EOGrow library, also an open source library, which we maintain. This enables the scale-up from, small regions to practically global data set. If you have too big to enable the analysis of big regions. Okay. So we have the full workflow here with the Earth observation data coming in, and with the EOLearn library taking care of the tasks for the workflow, and EOGrow for the scale-up of your application. Here's an example of such an application that use 3 different data sets, like in this challenge. So for building detection on satellite imagery, where we use the Sentinel-2 imagery, Airbus Spot and Airbus Pleiades to detect buildings on larger scale areas. More details, for more details, you can read our Medium blog post on HEACTOR. I would also like to present, this is a work in progress. It's a new project, and we are working on extending the Sentinel Hub with AI capabilities, where most of the machine learning infrastructure could be offloaded to Sentinel Hub. And I invite you all to visit us at the poster session tomorrow, where we will present this project, which is also in partnership with ESA. So our role in the AI4EO challenges is to support the challenge participants with the preparation of the machine learning ready data sets and with the starter toolkits in the form of Jupyter notebooks usually. So here's an example from previous challenges where we prepared the machine learning ready data set for the FISA2 and Imagine-E challenge. And these are the starter notebooks just to present the data and to get you started with the challenge. And now I will present the notebook we prepared for the Map Your City challenge, which is an exploration of the data set that we also prepared with Minder. So first in the notebook, I will just go through the notebook sections. So we present the dataset structure, which has been divided into the training and the testing set. And in the training set, you have the CSV file, and through that, you can, from the polygon IDs, you can then select the building or upload for all the buildings three images. One is the street view, the Sentinel-2 L2A, and the orthophoto image. In the training data set, of course, there's also the labels in a text file. And similarly for the testing data set, except the labels here are not there. So we also present the image formats and the structure. So the street view images are in JPEG format with the size of 512 times 1024 pixels. And they show the face view of the building, the facade. And we have two top view modalities. The first is the orthophoto in TIFF format of the size of 512 and 512 pixels with the resolution of 50 centimeters per pixel. And then we have the Sentinel L2A images, also in TIFF format, and with the resolution of 10 meters and with all the 12 bands. And the labels are, there are 7 different classes in the labels for the binned age of buildings. Okay, so in the notebook we then show how to load the data. We explore the CSV files. So we have the, this is the first is the training CSV file. For the training set, we have the labels, we have the country ID. So you will be able to know which polygons are within the same country, but you wouldn't know which country that is. And also this goes for the city. So you can, you could group by city or by country, but the geolocations have been hidden. So so you wouldn't know exactly where this location is. Okay, so then we visualize the data, the three modalities. The first is the street view, the orthophoto, and the Sentinel L2A. And here I have another visualization. So these are then organized so that the building is at the center, the blue dot. We have the orthophoto image covering 256 times 256 meters, and then the Sentinel L2A image, which covers 640 times 640 meters around each building. If we explore a little bit the training set, just we have the distribution by the 7 H classes, by the labels. We have the distribution by different countries and the distribution by cities. Just to explore a little bit how this data is distributed. It's not equally distributed over cities or countries. But still, this is the data set we prepared. So the format for the submissions should be a CSV file, including the PID of the original polygon, and the label for which the inference stage of your model put out as the result. And the evaluation metric for your solutions will be the mean producer accuracy, which is the average of the diagonal elements of the confusion matrix, according to inference on all modalities, plus a little boost with this number to be determined X, a little boost to give to solutions that have inference only on the top view modalities. And this is it.
Hello everyone, so I'm Nicholas, I work at the ESA Lab. I will talk about the baseline model, so you can use this new data set for machine learning, deep learning. So you have images, street view images, like the images you see in this slide. We also have top view images, and we want to use deep learning and machine learning models. For the baseline models, we have created two starting architectures, so we can use the residual network model, the model ResNet, which has convolutional layers and can model and capture local correlations. And also we have also prepared a transformer-based model, so the model segformer for classification, and transformer models can capture global correlations because they use attention. Regarding evaluation metrics, we have the confusion matrix and the average of the diagonal values of the confusion matrix. We also have the accuracy, precision, recall, F1 score. These are additional metrics, not for the leaderboard. The leaderboard is just based on the average of the diagonals of the confusion matrix. And the main aim is to model, to assess, to examine model generalization. So we have to evaluate the model on the held out cities. And this is the challenge. So the baseline models, two baseline architectures, the model ResNet and a transformer-based model, segformer for image classification. The loss function is the cross entropy loss, so it's a classification-based model. We have performed data augmentation, so horizontal flipping, cutout, Gaussian blur, and color jitter. And we have trained our models using adaptive momentum ADAM, and we have used Python and PyTorch. Okay, so we have two starting architectures: the residual network ResNet, which shows the specific architecture ResNet 152. We have also tried ResNet 50, for example, or ResNet 18. And we also have the transformer-based model, and we minimize the cross-entropy loss function. And the architectures and the models are modified by performing data augmentation and early stopping. And for data augmentation, for example, we see that we have performed Gaussian blur, for example, and other types of data augmentation. Okay, so regarding the results and the key results from these models, so the evaluation is on cities that are left out. So the evaluation is on data that we haven't seen during training, and also on cities that we haven't seen during training. In this case, so in the beginning we only use the street view images, so we start only with street view images and not with the top view images. And we evaluate the model, the residual network model in the beginning, so the model ResNet. We find its confusion matrix and then the mean of its diagonal values. And in this case, we see, for example, that the mean of its diagonal values is approximately 51%. We see that we also see that the mean, the average of the diagonal values, is a more challenging than accuracy, for example, or precision or recall, because we want to improve the performance for the middle classes. We also evaluate the second model, so the transformer model, the segformer for classification. We obtain the accuracy, precision, recall, and F1 scores. And in the next slide, we also have the confusion matrix for the transformer model. So we only use street view images again, and we evaluate this model, the transformer-based model, and we compute the confusion matrix and then the average of the diagonals of the confusion matrix, and in this case it's approximately 54%. Okay, so next we see the accuracy of the model with respect to the different countries and also to the different cities. So we examine what is the accuracy across countries and across cities. In this case, we show the accuracy on the 4 held out cities. So we have so the test set is 4 different cities from 4 different countries, and we see, for example, that that in a specific country, in country 3, for example, the performance is higher than, for example, in country 6. And we also examine the performance per country. The next step is to include 2 modalities, so having both the street view image and the top view image. So the next step is to consider both the street view images and the top view images, and this is known as data fusion. And this is cross-view processing, multi-modal processing, cross-view processing, and cross-view, having 2 cross views, so having both the street view images and the top view images. This is an open research area. And in this case, we train a specific model, the model ResNet, and we modify it to have 2 streams. So we have the input stream, which is the street view images, and the bottom stream, which is the top view image. And we concatenate the features in the latent space, so we perform late data fusion, and we perform classification at the end. Okay, so next we evaluate this model, we evaluate this data fusion baseline model. We obtain again confusion matrix and the accuracy, precision, recall, and F1 scores. So we have evaluated this specific ResNet 152 model, modified to have both street and top view images. And I think the key takeaway is that having cross-view inputs has benefits, so using both the street view and the top view has benefits instead of using only the street view images. So, for example, the average of the diagonals of the confusion matrix, in this case it is approximately 60%. In the previous slides we saw that for this specific residual network model, using only the street view images, the performance is approximately 51%, using the average of the diagonals of the confusion matrix. And then we also examined the following model, so having the data fusion model, but using only the street view images during inference, so training on both street and top view images, but using only the street view images during inference, and this is approximately 53%. So, so yeah, this is the challenge. So, what is the best overall system pipeline? There is room for improvement in the evaluation metrics, and specifically in the average of the diagonal elements of the confusion matrix. And this is an open question: what is the best overall system pipeline? Okay, so some suggestions to participants. Participants can use any model architecture, so for example convolutional neural networks or residual networks or transformer-based models, and yeah, they can use any architecture. Regarding the validation set, participants can use held out cities for the validation set, because in this way so the model will be evaluated on held out cities, so the validation set can have left out held out cities. Another recommendation is to have a smart data fusion mechanism. So in the baseline model we only have late data fusion, so we concatenate the features. Perhaps a smarter data fusion architecture can be used. Another suggestion is to perform segmentation to isolate the desired building. So the top views has a lot, both the street view and the top view have a lot of information, and perhaps using segmentation to isolate the building can increase the performance. Also, participants can examine and use regression rather than classification. So in the baseline model we used the cross entropy loss function and a classification model, but perhaps regression can also be used. And a model ensemble, so training several models and then combining them, can also be used. And regarding code, GitHub startup code will soon be available in the GitHub. Thank you very much.
Thank you. So the last important bit of information is how to participate, and then we'll go into the Q&A. So very simply put here, so right now we have this URL, which is most likely where the challenge will be posted on the website. But if that's not ready, you can go to the AI4EO, AI4EO.eu, and there you'll see past challenges and current challenges. And as soon as it's there, of course, you can sign in, join, and you can either create or join a team. That's up to you. Teams can range in many sizes. Try not to be a team of one. The idea is to be a team. And that's it. It's a very simple, straightforward process. And I'll go right into the Q&A then. Doesn't have to be a question specifically for me. It can be for my colleagues, any section. One moment for the recording. I believe we need the microphone. Yeah.
Hello. Good morning. Yeah, Robin Cole, Earth Daily. Obviously, a building can be modified over time, and you might, make additional changes to it. How would you then classify it? Would it be the earliest time, a later time?
So if the renovation is significant enough, would the building age be updated? Colleagues?
Well, this is actually a specific case because, of course, you can have an ancient building that has actually been renovated. Sometimes, even in the street view example that I put, it was pretty old, but it had photovoltaic panel. So actually, some cases we cannot say anything, of course. But in some other cases, there might be indicators that in the end enable you to really understand. Of course, it's a challenging problem indeed. Something that it's imposed from this perspective, but let's suppose that renovations are not dramatically significant in the amount of the example that we selected so far.
Right. And the ground truth for the age, that came from sort of historical records, or was that a human annotator that had some guidelines?
No, it's authoritative data sets, so what has been officially provided by the different countries. Of course, it's not perfect even in that case. So it might be human surveys there that have been doing it. So we have already seen that there were some inaccuracies. We tried at our best to exclude these, but it's large data set. So of course, it's something that we have to live with.
Okay.
Hi. I had a question about the train and the test set. You said because the test set is some held out cities. So have you ensured that in the training set at least those the other cities of the same country are included, or have you investigated the influence, for instance, country-specific architectural influences on building age?
I think it might be best if all of us come to the front so that we can use the microphone for the answers.
I think this is more for you than for...
Yeah, me or for Nicolas.
Please enjoy the hot seat.
Yeah, there are some held out cities in the test set, but I think the countries are all represented in both the training and the test set. But yeah, I would have to check the labels to get the distributions, but with the CSV files that will soon be available, you can then check how all the distributions are within the training and the test set and all the cross correlations with that. Okay.
All this by the data sets belong to countries that are also represented in the training. So it's not the same region, so
Yeah, we can say that it's pretty heterogeneous. I mean, we did our best to make it complicated, of course, which was also driven by the fact where data was consistently available. So you will see, I mean, if you scroll through the Street View data, it's pretty obvious, at least in which major areas we have been sampling so far. Yeah, so.
All right, and I had another different question about the EOTDL, I think, the datasets database. So is it also, I have a data set of Amsterdam of street level images with bounding boxes and also related building age, among other values. So would it be something that I could also upload there, or it doesn't work like that?
Yes.
All right, great, thank you.
So a longer answer, the idea of the EOTDL is that it can ingest many different data sets, and that if you have the bounding boxes and you have information like that, it would be linked to the metadata, so that just all these data sets can be grabbed by different people with the same sort of tools and filters.
Okay, great, thank you.
Any other question? Go ahead.
Yeah, on the EL40, I can't remember how you say it, that platform, how does stack feature into that? Is that like every data set must be a stack to go in, or is that just the flexibility there? Or?
So we would like to keep it as strict as possible. Of course, it's flexible to lose some of those stack tags individually. Right now, there's sort of 4 quality levels that will eventually be introduced. We're at Q0 now, which is really unmoderated, very flexible. Eventually, it will go to Q2, which is automated things like how many invalid data points there are, how many nons, that kind of thing. To eventually Q4, which is curated by a person to make sure that it's very machine learning ready. So there really is just a broad range eventually, and we'll see how everything shakes out and how much people adhere, because it is community-based, how much people adhere to that strict stack specification. And maybe you find in the end we have plenty of Q0 data sets where people wanted the storage, they have basic locations, but they didn't really put it into the perfect format. And then we have a small set of Q4 elevated data sets that we, as both the partners of the project and people, can also annotate and contribute. We even have a leaderboard about data contributions. So I hope that answers that.
Nice. And is the plan to also expose annotated data sets via Stack, or you see Stack as just a way to get data in?
Could you repeat that? Sorry.
Do you see Stack as being a way of sharing annotated data sets as well, or just a mechanism to get data into the platform?
No, sharing is definitely the goal.
Okay.
So that's a major proponent of that.
Okay. Good.
Question. We still have 20 minutes. I can stop before, but just to mention, yeah, in the 4 cities which are used for the test, there will be 2 for which we provide all the modalities. I mean, with the Street View and the Top View, and there will be 2 other cities for which we don't provide the Street View, so we just provide the Top View images. So that it encourages a little bit to work on, let's say, nice architecture over which eventually will train on all the modalities, but then the inference will be done only with the Top View. So you will have to be creative at some point. Otherwise, obviously, the performance will be lower if only using the Top View images, because you don't have this facade imagery. So that is part of the challenge as well, to come up with nice solution on that.
Has anyone in this room done an AI4EO challenge? Okay, good.
You should. So we'll refine, actually so far, I mean, the prices probably will give cash price, probably up to 5,000 euro for the first one, and usually provide also some vouchers. It can be through the network of resources, so access to Sentinel Hub, access to Pléiades imagery, Airbus information, stuff like that. So it has to be refined, and I think that will open the challenge in the coming 2 weeks. So stay tuned, and then you will see. And as we mentioned, it will be open for almost 4 months, so you will have to play the time to play with the data. And yeah, sure.
Based on just like what wins Kaggle competitions, it's usually large ensembles. You know, people with large compute budgets usually win those competitions. Is there, and obviously here you're going on a single score for, you know, the winner. Is there also consideration for different approaches which maybe are more efficient, or it would not require that kind of compute budget to complete? Is that part of the thinking, or it's all on this one score? Right. Yeah.
Just to say, we have not decided. There will be a privately level and publicly level.
Yeah.
So we will submit the solution, then there will be a split that will be done in the backend system, and then we will visualize with the public level, and then at the very end of the competition, we will display the private level.
Mm-hmm.
It's really funny because we will have some kind of smart split in the backend system. So that's we look for generalization.
Mm-hmm.
But yeah, I cannot really answer your question. Obviously, over the last challenge, sometimes we have people winning because they are obviously large
Yeah, true. Yeah.
And if that is a concern about budgetary restriction, the training data lab will offer GPU computing, so cloud computing, and that should hopefully narrow that gap between, you know, teams with large resources and teams with ThinkPad users.
Yeah. Cool.
Any further question? If not, maybe we can close the session, right?
Thank you all very much for attending.
Yeah. Thank you. And have a good week, enjoy. I guess we'll have some coffee maybe nearby. So I hope that you enjoyed the session. If you have any question, please, I mean, you can contact us through the website, which is AI4EO.eu, and then you can contact myself or any other one. We'll be able to help you on that.
Thank you.